Hello friends, in today's question, there is a circular tube in a vertical plane, two liquids which do not mix and of density d1 and d2 are filled in the tube. Each liquid subtends 90-degree angle at the center. Radius joining their interface makes an angle alpha with the vertical, then the ratio of d1 and d2 is. So we are given a circular tube, two liquids, density d1 and d2, and both of them subtend an angle of 90 degree at the center. So we have to find out the ratio of d1 and d2, that their respective density. So herein, as it is given that they do not mix with each other, so therefore you can say the pressure at the interface, because of the liquid density d1 and because of the liquid density d2, will be same. So we are going to use this thing and find out the ratio of d1 and d2. This question is comparatively, you can say, easy. The only little bit tricky part is find out the height of the liquid. That's the only little bit tricky, how to find out the height of the liquid. Okay. So let us first of all start by saying that in the question itself, it is given that the liquids do not mix. And are equilibrium at interface, and are at equilibrium at interface. So based on this, we can say that the pressure due to both liquid having density T1 and another density T2 at the interface is same. Therefore, pressure due to both liquids will be equal at the interface. So we can use the equation that if P is the pressure at the interface, then P will be equal to P naught plus rho GH, where this P is the pressure at the interface due to the liquid, P is pressure at the interface due to liquid, P naught is our atmospheric pressure, or in this case the P naught will be the pressure due to this vacant part. This is a particular question, but in general this P naught is taken as a atmospheric pressure. Atmospheric pressure. Rho is the density of the liquid. Density of liquid. G is the acceleration due to gravity. G is acceleration due to gravity, and H is the height of the liquid. The height of the liquid. So in this case we have two liquids. Let us call the pressure due to which is having density d1 is p1, and pressure due to liquid whose density is d2 is p2. And in this case it should be ideally mentioned because this tube is very, you can say, have negligible thickness, okay, so that we can easily find out the height, because if we include the thickness it becomes a little bit tricky. So we can say for liquid 2, which means with density d2. So let us redraw the figure. So we have two liquids, and this is the center of the liquid, and the vertical, it is making an angle of alpha, and this is the interface. So one liquid will be this one and another liquid will be this one. So this is our density d2 and this is having density d1. So we assume that this is point O. So this distance will be radius as well as this will be also radius. Okay. And let us draw a horizontal line which is in this direction. You can say just perpendicular to the vertical interface. So this angle will be also equal to alpha, and we say join this part and we also extend this part from here. So let us say this height is given as y and this height is given as y prime, and we call this as A, this is O, this point is A, this point is B, this is O, and this point is P, and this point is Q. So let me redraw the figure. This triangle part specifically here once again, this is point O, and this is point A, and we have a horizontal line. A perpendicular is drawn from A to this horizontal line. This angle is our alpha, and this is the vertical line which is joining, and the interface, this is our interface, sorry, it has to be somewhere here. This is our alpha, and we draw a vertical line like this. So this is our O, A and B, this is point P, and this is point Q. So this is 90, so therefore this angle becomes 90 minus alpha. Okay. And we know this is our, will be our radius, and this will be also our radius. Okay. So it goes something like this, and we are interested in finding out what will be our height of this d2. Okay, so therefore so this is our height of liquid d2, s2, from this point up till point A. So this is our S2, the height of liquid 2, and we assume that this from AB is y and this PQ is y prime. So from the figure we can say that our H2 is equal to y plus y prime. So let us remodify this equation for the liquid having density d2. So this is covering like this. Okay. So the liquid of density D2 is over this portion. So this is having density D2, and this is our density D1, which we will see that later on. So let us call this as equation number 1. So we can write that from equation 1, modifying it for liquid 2, which is having density D2. Let us call that pressure as P2. So this becomes our P2 will be equal to P0 plus D2 G, and height is given as H2. And like I said, written previously, that H2 is equal to Y plus Y prime. So let us find out what will be our Y and Y prime. So from here we can say that our if we take triangle OAB, in triangle OAB we can say that our sine of alpha Y can be written as R sine of alpha, and similarly in the triangle we have OPQ. You can write that Y prime is equal to R sine of 90 minus alpha. So we get Y prime is equal to R cos of alpha. So we substitute here, we get H2 will be equal to R sine of alpha plus R cos of alpha, which can be written as taking R as common. So this will be sine of alpha plus cos of alpha. Therefore our P2 will be equal to P0 plus T2 G R sine of alpha plus cos of alpha. So we found out the pressure at the interface due to density D2. So we can say P2 is the pressure at the interface due to liquid 2. Liquid 2 means with density D2. Now let us find out, for same analysis we are going to do for liquid 1. For liquid 1, which means having density D1, and in this case also we are going to find out what will be its height. So let's draw once again. And let us put this is center O, and we drew, and this is our interface. So we have this as D1, and this was our D2, and this angle was alpha, and we just said that this is our Y and this distance is our Y prime. Okay, and let us draw joining this line. So this angle will be also equal to alpha, and we say that this height is x. So the height of the liquid will be equal to this height. Okay. So let me redraw this figure, and let us call this as point as L and this point as M. And we already know this point is A, this is B, this is P, and this is Q. So let us redraw the figure again. So this is point L connected to point O, and there is a vertical line. This one we are calling it as M, and this will be our pipe, and we have the interface. This angle is alpha, and here this is our y prime. Okay, this is point our P, this point is our Q, and this is our y prime. And we said let OM, this distance is given as x. So this is alpha, so we are going to have alpha because the angle subtended by it, each liquid at the center is 90. So we are interested what will be the height. So the height of the liquid will be this one, that is our H1. Okay, so we can say that our H1 will be equal to, we are going to have it as y prime minus x. That will be our H1. Okay. Let me, I think, yeah. So y prime we already found out that y prime was our equal to r cos of alpha, and this distance is r. So we can say in the triangle we have LOM, we get x will be equal to r sine of alpha. So we get our H1 will be equal to, taking r as common, this will be equal to cos of alpha minus r sine of alpha. Okay. This figure is, I think, somewhat okay. So we can understand from here also that this and this is our y prime, and we have taken that this distance is x. So the height will be over this part. Okay, so the thickness of this pipe is very small, so this will be H1. Okay, this figure is little bit, you can say, not looking good according to the formula, but from here we can say that our H1 is equal to y prime minus x. Okay, so this is more clear. So this is our y prime, and this distance we have taken as x. So the height is our H1 is y prime minus x. Okay, it doesn't look from here, but from the main figure which is given, clearly understood that H1 is equal to y prime minus x. Okay. So similarly, we are going to modify equation 1. So we can say from equation 1, modifying it for liquid 1, which is having density d1. So we can write this as P1 is equal to P naught plus T1 H1. We found out our H1, so we can write this as P naught plus D1 G R. We get this as cos of alpha minus R sine of alpha. So let me write it again here. This is P1 is equal to P naught plus D1 G R. Sorry, R is not here. We get this as cos of alpha minus sine of alpha. And this P1 is the pressure at the interface due to liquid 1. P1 is the pressure at the interface due to liquid 1. Due to liquid 1, which basically means whose density is D1. So this is our equation number 2, and we have this as equation number 3. So like I previously mentioned, that the pressure at the interface is same. Okay. So you can say that pressure at the interface is same. Therefore, from equation 2 and 3, we get P1 is equal to P2. P1 is equal to P2. Substituting value of P1. P1 was our P naught plus D1 G R, and we have cos of alpha minus sine of alpha. P2 was our P naught plus D2 GR, and we have cos of alpha plus sine of alpha. P naught and P naught cancels out, so we get this as D1 GR cos alpha minus sine alpha is equal to D2 GR cos alpha plus sine alpha. GR and GR cancels out, and we have to suppose to find out a ratio of D1 by D2. Therefore, we get D1 by D2 is equal to cos of alpha plus sine of alpha divided by cos of alpha sine of alpha. We can take cos of alpha as common from numerator as well as denominator. So we get this as cos of alpha 1 plus sine alpha divided by cos alpha divided by cos alpha 1 minus sine alpha divided by cos alpha. Cos and cos cancels out, so we get D1 upon D2 is equal to 1 plus tangent alpha and 1 minus tangent alpha. So this is our ratio of the densities D1 and D2. So the option available in the form of the tangent is option number C. So therefore you can say that option C is correct. Option C is correct. This completes the question. Thank you.